In the darkness between planets, something the size of a city block breathes out glittering jets, yet its path barely twitches. Thrusters without a shove, a sail without a breeze. Telescopes see activity that should push. Orbital fits answer with near silence. If the force is real, where did the motion go? Stay with this, because the simplest rules of spaceflight seem to bend, and the reason why could redraw the border between the known and the unknown. Imagine standing on a frozen lake with a pressurized hose in your hands. Every spray kicks you the other way. That is rocket logic. Space follows the same rule. When ice on a sun-warmed surface turns to gas and shoots into the void, recoil should nudge the source. Astronomers use that tiny nudge all the time. They watch active comets drift away from gravity-only trajectories by a whisper, then convert that whisper into mass flow, vent geometry, and thermal behavior. The quantity has a name that sounds dry, non-gravitational acceleration. In practice, it is the signature that outgassing is doing work. It is the tell that turns a glow into a force. Our visitor breaks the rhythm. Telescopes report a living coma, a halo of gas and dust. Images show a plume that faces the sun, then a tail that stretches the familiar way. Spectra reveal molecules that only appear when fresh material is being released. The scene looks textbook, yet when teams stack weeks of precise positions and solve for motion, the expected non-gravitational term does not rise above firm detection. There are upper limits, careful caveats, and a lot of double-checking. The residuals, those little differences between a gravity-only path and reality, should drift in a consistent direction if thrust is unbalanced. Instead, they sit near zero within the noise, or wander without a clear push. Why would activity fail to write itself into the orbit? One possibility is mass. If the nucleus is far heavier than its glow suggests, the same jets produce a much smaller acceleration. A cargo ship barely notices a garden hose. Another possibility is symmetry. If multiple vents fire in patterns that cancel, the total thrust can drop while the spectacle remains. Think of 4 people on skates pushing a platform from opposite sides with equal force. The platform shines with effort, but it hardly moves. A competing view suggests that we are still early in the measurement arc, that the signal will emerge over a longer baseline as heating increases. It remains uncertain whether any single explanation covers every clue, and the responsible attitude is to test all 3 against new data. To feel the stakes, remember that non-gravitational acceleration is not an exotic trick. It is the quiet workhorse of comet dynamics. Missions like Rosetta have flown through jets and watched trajectories change. Giant comets like Hale-Bopp still showed measurable accelerations during their famous displays. In those cases, the numbers fit the picture. Here, the picture defies the numbers. That is why engineers and dynamical modelers keep circling back to the paradox. If thrust is present, where is the accumulated effect over time? If thrust is absent, what is powering the spectacular coma and evolving tail? There are practical reasons to be cautious. The inner sky, near the direction of Sagittarius, is crowded. Early measurements can be tricky when star fields are dense and the object is faint. A coma can mask the tiny point of the nucleus, so photometry can mislead size estimates. Even sunlight pressure on dust can confuse casual fits if the data are not cleaned well. Evidence is limited, but one inference is that multiple small uncertainties can combine to hide a small but real acceleration. That is why several teams pursue independent reductions, and why they publish limits alongside their best fits. If you need an image, picture a chalk line on a dark floor. That line is the gravity-only path, smooth and patient. Now, picture a transparent hand, pressing gently on the traveler. Over hours, nothing changes. Over weeks, a subtle curve appears. That curve is the non-gravitational term. With this object, the chalk line and the real line still nearly overlap. Either the hand is very weak, or there are 2 hands pressing in opposite directions that nearly cancel, or the traveler is much more massive than its glow implies. A minority view holds that artificial control could neutralize a natural push, the way reaction control thrusters hold a station against drag. The idea is interesting as an engineering thought experiment, but it must wait behind natural pathways. No direct signature of devices exists in public data. No resolved image shows geometry beyond geology. The scientific way to handle an idea like this is simple. State it, set criteria that could disprove or support it, and put it back on the shelf until the sky forces our hand. For now, the paradox is enough to carry us. Activity without the expected shove. A city block of ice and rock that looks alive but refuses to drift in a measurable way. In the next chapter, we will make the invisible visible and show how non-gravitational acceleration usually reveals itself and why its absence here is so provocative. Picture a skater holding a bottle that leaks in a steady thread. The skater drifts the other way, not because the leak is violent, but because it never stops. Space is filled with versions of that quiet nudge. Sunlight pushes on dust and ice with gentle pressure. Subsurface ices warm, turn to gas, and rush out of cracks as unseen jets. Each jet is a tiny engine. Over hours, the push is nothing to brag about. Over weeks, the push becomes a path you can measure. Astronomers treat these pushes like a second alphabet written on top of gravity. Once you know the letters, you can read what a body is made of, how it rotates, and how its surface breathes. The grammar begins with 2 tracks. Gravity-only motion is the ideal curve carved by the pull of sun and planets. Non-gravitational acceleration is everything else, a collection of whispers from sunlight, thermal re-radiation, and outgassing. The trick is that you cannot strap a force meter to a comet from Earth. You infer the force by watching position, again and again, against background stars that act like pins on a map. Each precise position is a bead. A month of beads builds a necklace. If a comet is active, the necklace will not lie perfectly on the gravity curve. It will sag a little to one side or float a little high. That offset is the signature of the tiny forces at work. There are clean cases that teach the rules. When Rosetta escorted a small comet, mission planners had to account for thrust from jets, or the spacecraft would drift off the planned path. The jets were visible in images, they were audible in the trajectory math, and the two agreed. A bright giant from the late 90s taught a similar lesson at a different scale. Even very large bodies respond to their own breath, slowly but measurably. Those examples gave the field confidence that the language of tiny forces is not poetry. It is accounting. Inputs and outputs match within sensible error bars. The sunlight piece is the simplest to imagine. Photons carry momentum. When they strike a surface and bounce or are absorbed and re-radiated, they exchange momentum with the object. The effect is small but constant, and it has a known dependence on distance from the sunday. Outgassing is more dramatic in its geometry. If one region heats and vents more strongly than others, the recoil points in a preferred direction for a while, then changes as the body rotates, then changes again as the seasons shift. That time variability is a gift to observers. It writes a pattern into the residuals that you can model. Fit the pattern, retrieve the rotation state and likely vent distribution, then check if the chemistry agrees. Chemistry matters because different ices wake up in different ways. Water likes strong local vents that produce narrow jets. Carbon dioxide often escapes more evenly across broad areas, especially when the crust is porous. Even if both species are present, the balance between them sculpts the way thrust adds up. If many small sources breathe together, the pushes cancel to a degree. If one or two sources dominate, the pushes align and build. The result is a net acceleration that you can pick out of the data with patience. Patience is the price. Individual measurements can carry noise from crowded starfields, from atmospheric turbulence for ground-based work, or from the halo of dust that blurs the point at the center. No single night decides the case. The power comes from accumulation. Stack nights across different geometries. Watch the curve grow a tail in the residual space. Once it clears the noise, it tends to stay clear. That is why the absence of a clear non-gravitational term in our current object is not a footnote. Enough time has passed to expect at least a trend if the thrust is strongly asymmetric. There are caveats that keep modelers humble. Early arcs can fool you if a handful of points sway the fit. Coma-dominated images can bias centroids away from the true nucleus. Sunlight pressure on dust tails can masquerade as motion, if not separated from the nucleus signal. Experts remove or correct these effects through careful reduction. Even after that work, the method has proven itself on many active bodies. Which brings us back to the paradox. We see venting, We see structural changes in the coma and tail that say energy is flowing. Yet the necklace of positions still hugs the gravity-only curve within tight limits. Understanding how tiny forces usually reveal themselves sets our baseline. In the next chapter, we follow the path of discovery itself, because where the object came from and how we first noticed it help explain why the signal is so challenging to read at all. The story of this object begins with a quiet blink in a crowded sky. Imagine a river of stars flowing from the direction of Sagittarius, field after field packed with points so dense that any moving speck must thread a maze of glitter. Automated survey frames patrol this river each night, not for beauty, but for motion. Software compares fresh images to the previous sweep. A small dot shifts against the background. It raises a flag. Human eyes follow. Then the process repeats with more frames and longer baselines. That is how the hunt often goes. One night reveals a hint. The next night turns a hint into a trend. The early frames that include our visitor were exactly that kind of tease. A nothing that began to look like something, then refused to sit still in a way that fits the family of bound objects. The first calculation that made astronomers lean forward was the shape of the track in time. Instead of the gentle curve that belongs to a resident of our system, the motion hinted at a path that would never loop back. Hyperbolic is the word, which simply means the sun will not keep it. It is a signal of origin rather than destination. Observers at other sites picked up the thread and placed their own markers on the sky. Each marker is a timestamp and a position, and each pair shrinks the space of possible paths. Within days, the consensus settled. Incoming from beyond, outbound again soon, an interstellar visitor has joined our archive of brief encounters. Finding anything new among the star crowd near the galactic center is a small victory. The density of background sources demands careful subtraction and clean astrometric solutions. The instrument must know exactly how its pixels map to angles on the sky. The night must offer enough stability that the point spread function remains consistent. Even then, the object can masquerade as a slightly smeared star if the coma is already active. That is why the earliest few detections can feel ambiguous. You can believe an object is there, yet not be sure what kind of object it is. The spearman of certainty rises as more frames arrive from more telescopes under more conditions. Archival searches add weight to the timeline. Once a track exists, teams go backward into stored images and look along the predicted line for faint appearances that were ignored at the time. Recoveries like this extend the arc. They give the orbit fit more leverage, and they improve the separation between gravity, only motion, and everything else. For this visitor, an archival sweep produced a handful of faint points that matched the predicted path. That is how we learned where it was before it became a headline. It was already here, sliding across the canvas, a whisper too quiet to hear until a computer raised its hand. The geometry of discovery matters because it builds in blind spots. Sagittarius is beautiful, and it is also unforgiving. A small cometary coma blends into mottled star fields, and the lingering glow of dust can bias the measured center away from the true nucleus. Photometry taken in such conditions can overstate brightness or mask small changes. Astrometry can inherit tiny shifts from the under-resolved core. None of these problems are fatal to good science, but they slow the climb from suspect to measured effect. They also explain why the same dataset can support two honest readings. Activity is visible, yet the non-gravitational signature stays at the edge of detection. Dates and distances temper the mood. From the start, analysts flagged that this is not a hazardous approach. The Sun will receive the closest pass at about 1.5 Earth-Sun distances. Earth will watch from a safe margin near twice that span. These facts pull fear out of the frame, which makes room for a different urgency. The clock is running not because danger rises, but because information peaks. Heating climbs as the object rounds its turn, and chemical species wake in different orders. Telescopes, both on the ground and above the atmosphere, must secure observation, time before brightness declines and geometry grows unkind again. A single-sentence reorientation of the through-line is useful here. We are chasing a simple paradox, activity without the expected push, so each chapter builds the tools and context we need to test whether mass, or symmetry, or measurement limits hold the answer. The discovery thread hands us a map and a deadline. We know where the visitor has been and where it is going. We know that early measurements were made in a field that complicates clean answers. We know that the time to resolve uncertainty is short. With the path now drawn across the calendar, the next step is to look at what the changing geometry of the inner system guarantees, what it does not, and why safe distances do nothing to reduce the scientific stakes. Start with a picture of the inner system as a clean clock, the Sun at center, Earth and Mars as slow-moving hands. Our visitor enters the scene on a tilted track that never comes close to either world. That simple map answers the fear question with clarity. Closest approach to the Sun sits near 1.5 Earth-Sun distances. Earth remains comfortably farther out, near twice that span. There is no impact corridor. There is no hidden bend that would steer danger our way. Safety is the easy part. Urgency is harder, and it comes from geometry and time. Comets and interstellar visitors speak when the Sun heats their surfaces. The voice is chemistry that turns cold into vapor, and vapor into jets and halos. That voice grows loud only for a while. The shape of the orbit decides where the light is good and where it is poor. Angles decide which side of the body we can see, and how far a dust sheet tilts into our line of sight. Even a safe flyby can be a once-only performance. The viewing season closes as the object rounds the Sun and slips into glare or distance. What we miss now, we do not get back. Think about what the calendar guarantees. As the object approaches its point of maximum, heating, sublimation increases. Weak spectral lines brighten, features in the coma become crisp. Structures in the tail react to radiation pressure and to the shift in our viewpoint. These changes sharpen diagnostics. If there is a small non-gravitational term that tracks activity, late season is when patience is most likely to pay off. If symmetry keeps the net push near zero, stronger activity may still leave the orbit quiet, which is a result of its own. Either outcome narrows the space of truth. Geometry sets traps as well as gifts. The line from Earth to the object, and the line from the object to the Sun, create a phase angle that can hide or reveal details. A high phase angle can exaggerate a sunward plume. A low phase angle can make a dust sheet look like a thin tail. In some configurations, the coma washes over the nucleus and drags the measured center away from the physical core. That shift is small, yet it matters when the signal we seek is also small. Observers plan around these traps. They space out measurements to sample different angles. They pair ground-based nights with space-based windows to escape atmospheric noise. They record in filters that separate gas from dust, then recombine the story with care. Safe distance does not mean dull data. In early October, spacecraft at Mars enjoy a vantage that Earth cannot match. A camera off to the side reads the same scene from a fresh angle. That oblique look can test whether a plume sits on one hemisphere or wraps around the body. It can test whether small structures in the tail are perspective tricks or true filaments in the flow. Any improvement in orientation knowledge feeds back into the dynamical fit. The more we know about which regions receive heat and when, the better we can model what the thrust should be, and then compare that model to the nearly silent residuals. The orbit diagram also marks the hour when glare takes the stage. The weeks around closest approach are not simply bright. They are also complicated by low elongations from Earth that make daytime or twilight observations necessary for some setups. Teams request time on telescopes that can chase near the Sun without burning detectors or saturating the field. Others wait for darkness at a different longitude. Coordination becomes as important as technology. The object will not pause for anyone. The clock keeps turning. All of this explains why scientists can sound both calm and urgent in the same sentence. There is no danger to the public. There is a rare alignment that could answer a physics question cleanly. That question sits at the heart of comet dynamics. Why does visible activity fail to produce a clear push in the orbit? If the answer is mass, we will learn something about compact formation in other systems. If the answer is symmetry, we will refine how chemistry sculpts thrust on porous surfaces. If neither answer is sufficient, we will widen the search with better defined limits. The safe map now flows into the first images that puzzled everyone. Early plumes appeared to point toward the Sunday. Later views showed a tail streaming away as expected. Nothing supernatural lives in that reversal. It is a lesson about perspective that often fools the eye. To understand how an anti-tail can appear, and why it does not imply backward thrust, we need to slow down and watch dust behave on a stage built from angles and time. At first glance, the images look like a prank. A pale spear of dust seemed to point toward the sun, the very direction that comet tails are supposed to avoid. Viewers whispered about engines and reversal and unknown physics. The truth is stranger in a quieter way. An anti-tail is a trick of geometry and timing. Dust does not feel embarrassed by names. It follows the simple rules of sunlight and momentum. When we stand at just the right angle and at just the right moment, a sheet of dust that has spread along the orbit can appear to point sunward. The dust is not marching. Upstream. We are looking across a sheet that has rotated into our line of sight. Picture the orbit as a ribbon sprinkled with flour. Weeks before the dramatic photo, grains left the surface during an earlier episode of heating. Those grains lag slightly behind or run slightly ahead, depending on the size and the push they receive from radiation pressure. They spread into a thin fan that hugs the orbital path. As the geometry changes, Earth can slide into a view that lines up that fan with the sundae. The eye reads a ray pointed inward. The physics offers a shrug. Nothing about the underlying forces has changed. The grains still feel sunlight pushing them away from the star. The viewer has moved to a balcony where perspective plays illusions. This is not a new lesson. Several comets in the historical record have flashed anti-tails for a few weeks, then replaced the strange spear with the familiar sweep away from the sundae. Our visitor followed that playbook. Early frames showed a faint sunward spike. Later frames revealed a traditional dust tail that lengthened and curved. The transformation teaches two ideas at once. Activity was real, since there was enough material to sculpt a visible structure. Perspective was powerful, since changes in alignment altered the silhouette in a way that could fool a casual viewer. Understanding the stagecraft of anti-tails matters because it inoculates the story against a common misread. If you think backward-pointing dust implies thrust toward the sun, you might expect bizarre non-gravitational behavior in the orbit. No such implication follows. The tail geometry does not dictate the direction of recoil. The recoil depends on where jets exist on the surface and how the body rotates. The tail is largely a story about dust, grain sizes, and radiation pressure and viewing angle. The orbit cares about the integrated momentum carried away by gas. Those are related, but not identical layers of the same system. The gas story is quieter to the bluffed eye, but it holds the key to thrust. Gas leaves the surface at high speed and spreads much more quickly than dust. It writes its presence into spectra rather than into high-contrast shapes. Instruments see lines that brighten as heating climbs. Instruments also see which molecules lead the parade. For this object, carbon dioxide often dominates over water. That composition may encourage more even release from many locations, rather than from a few jets. If so, the net push can shrink while the display remains impressive. The anti-tail episode also tested the discipline of measurement. In crowded star fields, the sunward spike can stretch across the very pixels used to compute a center for the object. If observers are not careful, the calculated position can be pulled a little toward the bright spike. That tiny shift would be enough to mimic or mask a small acceleration term, especially over short baselines. Teams addressed this by modeling the coma and subtracting the dust structure before measuring the centroid again. They repeated the process in different filters that favor gas or dust. They compared results from separate nights and separate instruments. The work is tedious and very necessary, because our entire paradox rests on whether the orbit deviates from the gravity-only path by a small but coherent amount. By the time the dust settled into a more traditional tail, the narrative had gained clarity. The early sunward look was a perspective effect that comes and goes. The later frames confirmed that solar radiation pressure and the solar wind were sculpting material in the expected direction. Nothing in these pictures rescued the missing non-gravitational term. If anything, they deepened the puzzle. Activity looked vigorous. Structures changed on timescales that matched rising heat, yet the accumulated push remained hidden in the residuals. We are left with a simple handoff. The sky has shown us that anti-tails are part of the normal repertoire of cometry, appearances. We can set aside that distraction and return to the ledger. Months of active behavior should add up to a measurable force if the vents are strongly unbalanced. The next chapter asks why the residuals still whisper near zero, and what that silence tells us about mass, symmetry, and the limits of our sight. Begin with the simplest expectation. If a body is venting, a small but steady acceleration should reveal itself as a bend in the record of positions. Astronomers do not look for a dramatic swerve. They look for a drift that grows by millimeters per second over weeks, then by kilometers over months. To extract that drift, teams fit a gravity-only path to the observations, then study the leftover differences. These leftover differences are the residuals. When a comet is active and asymmetric, the residuals tend to march together in one direction. When the activity is balanced or weak, the march slows and the cloud of points loosens into noise. Our visitor has delivered mostly quiet cloud, not a march. This quiet does not come from a lack of effort. Observers have collected positions from multiple sites, at different times of night and with different filters. They have reduced images with coma models that try to isolate the light of the unresolved nucleus from the brighter halo around it. They have removed bad nights. They have flagged frames with elongated stars. They have compared independent pipelines. The headline stays the same. Activity is obvious in images, yet the non-gravitational term in the orbit solution remains at or below the common detection thresholds. That result is not proof that the true term is zero. It is a statement that any existing term must be small enough to drown in the current noise. Why is the noise large enough to hide a whisper? One reason is geometry. Early and mid-season views pass through crowded regions where the background changes on scales similar to the size of the coma. A slight mismatch in how the background is subtracted can pull the measured center by a fraction of a pixel. Over one night, that is harmless. Across a month, that becomes confusion about whether a shift is a real force or a residual of image processing. Another reason is the contribution of dust to the central light. Dust close to the nucleus smooths the brightness profile and makes the point more blob than pin. The centroid then depends more on the shape of the model than on the body itself. That sensitivity introduces a subtle bias that is hard to quantify without a resolved core. There is also the issue of cadence. Every arc has gaps due to weather, telescope schedules, and simple daylight. Small periodic effects from rotation can hide inside those gaps. If a jet points sunward for a few hours and then away, the net effect in the residuals can average down. Over time, the signature is still present, but it looks like a slow breathing rather than a steady push. Modelers can recover such patterns, but they need dense coverage or a strong prior on the rotation period. At present, both ingredients are limited, and the residuals remain ambiguous. None of this removes the paradox. Many comets have been measured under less friendly conditions and still show a clear non-gravitational term. So the question becomes, what special features could keep this case quiet? Mass is one candidate. If the nucleus is very heavy relative to its outgassing, then every puff produces less change in velocity. The same plume that would move a small body by a visible amount would barely nudge a mountain. Symmetry is another candidate. If the surface hosts many small vents that activate together, and if rotation distributes sunlight evenly enough, then the vector sum of all those tiny kicks can shrink to a near cancel. The coma would flourish, the orbit would not. A competing view suggests that we have not yet reached the point in the orbit where the pattern emerges. As the object approaches its closest distance to the Sun, outgassing should intensify. If there is any inherent imbalance, it will be magnified. If the residuals begin to curve, that would confirm that the silence was only temporary. It remains uncertain whether the signal will emerge. The community has prepared for both outcomes. Telescopes are scheduled across longitudes to catch short visibility windows near the Sunday. Teams have shared reduction recipes and test frames to reduce method disagreement. The goal is not to force a conclusion. The goal is to push the precision to the level where nature must choose one path. There is an important philosophical point hidden inside the math. An upper limit is not a failure. It is a fence built around possibility. If the non-gravitational term remains below a given number, then the product of mass flow and vent asymmetry must also remain below the corresponding value. That fence trims the garden of hypotheses. Extremely unbalanced vent maps become unlikely. Very low mass scenarios become difficult to defend. carbon dioxide dominance becomes an attractive natural way to maintain spectacle without strong net thrust, since broad release patterns tend to cancel. Each constraint narrows the space until only a few shapes of truth can fit. For viewers, the silence in the residuals can feel unsatisfying. The coma dances, tails grow and twist, metals rise in the spectrum, and yet the orbit sits patiently on the chalk line of gravity. That calm is not the end of the story. It is an invitation to examine the chemistry that sets the stage for symmetry. If the gas mix favors even flow, the numbers should support that. If an unusual metal signature hints at a special pathway for dust and gas, the timing of those lines should agree with a symmetric release. The next chapter turns to that chemical ledger, where nickel shines while iron hides, and where carbon dioxide speaks louder than water. In that ledger we may find why the force is real, yet the motion stays small. When you look for a compass in a strange landscape, you grab the last two landmarks that everyone agrees on. For interstellar visitors, the first landmark is the elongated Scout from 2017. The second is the Dusty Messenger from 2019. One offered a push without a visible cause. The other offered a visible cause with a matching push. Together they define the ends of a spectrum, and our present object sits between them like a riddle that borrows traits from both while matching neither. Begin with the first. Telescopes caught a small object on a hyperbolic arc that flashed through the inner system and then faded. No coma showed up in the images, no broad cloud of dust, no obvious jets or fans. Yet when teams fitted the positions, the path carried a measurable non-gravitational term that did not collapse under statistical checks. The magnitude changed with distance from the sun in a way that felt familiar, as if sunlight or some quiet release were at work. What made it provocative was the absence of the usual signs of outgassing. The acceleration was there. The expected gas and dust were not. The community produced natural ideas to explain the mismatch, including radiation pressure on a high area to mass shape, or outgassing that left no common traces. And the debate narrowed to which was most plausible rather than whether the numbers were real. Now hold the second landmark in mind. A faint speck brightened into a classic comet with a coma and a tail that required no introduction. Spectra recorded water and carbon monoxide and other familiar molecules. The orbit solution picked up a non-gravitational term that grew and declined with activity. The case felt like a control experiment delivered by the sky. Interstellar origin did not break the rules. The same physics that governs native comets applied. The push matched the breath. The fit was satisfying in a way that comforts engineers and modelers. You could predict what the data should do and watch the data obey. Our current visitor asks a different question. It shows activity that nobody disputes. Telescopes see a halo. Images record plumes and an evolving tail. Spectra report strong carbon dioxide and rising cyanide. The picture promises a shove in the math, yet the fitted orbit sits close to the gravity, the only solution within the present uncertainties. The net push remains faint or elusive. So we have three cases that sketch a triangle, one with push but little visible cause, one with visible cause and matching push, one with visible cause and little measured push. The map tells us that interstellar visitors do not come in a single flavor, and that our rules must allow a range of behaviors shaped by composition, geometry, and time. A single-sentence reorientation is helpful here. We are testing a paradox that sets visible activity against a quiet orbit, and the two earlier visitors show that both sides of that equation can vary more than intuition suggests. What do these bookends buy us beyond perspective? They supply constraints on any claim about our present object. If someone argues that interstellar origin alone makes non-gravitational effects unpredictable, the Dusty Messenger says otherwise. If someone argues that a lack of visible gas makes a measured acceleration suspect, the elongated Scout says otherwise. The lesson is that evidence can be real even when it confounds habit. The right response is not to discard the outliers, but to ask what natural factors can reproduce them within the rules. Composition is one candidate that threads all three cases. A body rich in carbon dioxide may breathe across wide areas, which can cancel net thrust while still lighting up spectra. A body that lacks easy tracers might still vent a transparent species, which can push without announcing itself in common lines. Geometry is another. Rotation can expose different surfaces in patterns that average down residuals in one case, or drive periodic terms that stand out in another. Time is the third. Short observing arcs can miss the phase where the signature climbs past a threshold, while long arcs can lock a pattern in. By placing the new puzzle between two well-studied extremes, we protect ourselves from sloppy thinking. We can accept that the odd is possible without leaping to exotic answers. We can accept that the familiar is possible without ignoring inconvenient data. The next step is to anchor these ideas in the closest thing to laboratory truth that astronomy offers. That means a comet where a spacecraft flew through the breath and measured the shove at the same time. If astronomy ever had a lab bench for comet physics, it was the Rosetta mission. A spacecraft arrived at a small, oddly shaped nucleus and lived there through seasons. Cameras watched jets as they flickered and roared. Instruments tasted the gas and dust directly. Navigation teams felt the tug of outgassing in their trajectory solutions and fired thrusters to correct for it. This was not inference from far away. This was cause and effect written into the flight plan. Heat the surface, vents open, molecules escape, recoil pushes the source, and a measurable change appears in the path of a companion spacecraft. The chain is complete from sunlight to force to motion. That is why Rosetta sits at the center of any argument about what activity should do. Consider what those maps of jets revealed. They were not smooth halos. They were patchy and directional. Narrow curtains of material emerged from cliffs and pits. Some rotated into and out of daylight with the spin of the nucleus. Some woke only when the angle of the sun crept to a seasonal sweet spot. Each jet produced a local thrust vector. Add them all and you get a net push that might wander through the day, yet it rarely vanished. The spacecraft felt that push as a slow drift from its intended orbit. Modelers could predict the sign and sometimes the size of that drift when a particular region lit up. That concurrence between image, physics, and navigation is the gold standard. It shows that visible activity and dynamical effect are twins more often than not. Now, lift the view from a few kilometers to the scale of a great comet. During the late 90s, a bright visitor with a large nucleus dominated skies for months. Its coma bloomed into a planetary-sized sphere. Its tail painted a broad brushstroke across morning and evening. The body was large, much larger than the nucleus Rosetta studied. If size alone could swallow thrust, that would have been the case to reveal it. Yet observers still measured non-gravitational effects, small compared to its spectacle, but present and coherent. The heavy body did not shrug off its own breath entirely. It flinched slowly, and careful fits could see the flinch. That lesson stitches directly to our current paradox. Inertia damps, it does not erase, unless something else helps it cancel. The step from these truths to our case is not a leap, it is a comparison. Rosetta proves that jets concentrate, and that thrust is measurable with direct sensing. The giant comet proves that large mass reduces, but does not eliminate the signal. Put those together, and two routes remain open for a quiet orbit under active conditions. Either the mass is much larger than the glow implies, enough to turn the push into a whisper below current sensitivity, or the venting is distributed in such a symmetric fashion that vectors cancel to an unusual degree while the total flow stays high. Both options are natural, and both require evidence that can be tested with data that we can gather in the window ahead. There is another gift from Rosetta that matters here. It gave us a playbook for how dust and gas partition their stories. Gas leaves fast and writes its lines into spectra. Dust lingers and writes its shapes into images. The nucleus sits buried in a glare that tempts even skilled teams to overestimate its size. Separation of these layers demanded models that were validated by the spacecraft. Those models now serve ground-based and space-based observers who must split light into components without the luxury of a close escort. When teams say they have removed a dust structure before measuring a position, when they say they have used filters that isolate a gas band to refine a centroid, they are using tools that Rosetta helped calibrate. What about the role of composition? Rosetta and other missions confirmed that water often drives narrow jets from specific terrains, while carbon dioxide and carbon monoxide can seep more broadly. A surface that leaks water from a few hotspots will kick like a one-sided engine. A surface that exhales carbon dioxide from many pores will glow without a strong direction. If our current visitor is rich in carbon dioxide relative to water, a more even release becomes plausible. That would reconcile activity with a small net push. It would not demand exotic physics. It would only demand that formation and thermal history favored one volatile over another. The giant comet adds a final caution. Spectacle does not simplify measurement. Bright comae and long tails delight the eye and drown the nucleus. The bigger the show, the more important it becomes to treat the unresolved core as a separate actor hidden inside the light. If the core is small, the same glow means a lower albedo or more dust. If the core is large, the same glow means a higher albedo or less dust. Those unknowns propagate directly into any calculation that tries to connect outflow rate to mass through the vehicle of acceleration. That is why improved constraints on size and reflectivity are not luxuries. They are central to deciding whether mass or symmetry is the better key. We have put our hands on the lab bench and on the giant stage. Both speak the same language. Jets exist. Outgassing pushes. Size matters, but it does not null the rule. The only ways to mute the signature are extreme inertia or near-balanced geometry, or careful, the combinations of both. With that frame in place, it is time to open the chemical ledger for this object in particular. In that ledger, a bright nickel signature whispers while iron stays shy, and carbon dioxide sings louder than water. The pattern is odd, and its implications could explain the quiet path. The spectrum came back like a coded postcard, bright with lines that should travel together, yet one companion was missing. Nickel glowed, iron stayed quiet. On another axis, carbon dioxide rose as the leading voice while water played a supporting part. Chemistry is the handwriting of a comet. It records where the body formed, how the surface changed during long travel, and which parts of the crust answer first when sunlight arrives. This handwriting looks unfamiliar. Unfamiliar does not mean unnatural, but it does ask for patience while we test the ways that nature can produce such a script. Start with the metals. Nickel and iron often move in step, forged in similar furnaces long before any comet ever existed. In many comets, neutral nickel and neutral iron appear together as faint lines that brighten with heating. Here, the nickel lines stand out while iron hovers near the detection floor. One possibility is that space weathering has altered the outer grain population so that compounds carrying nickel are liberated more easily. Ultraviolet light can break apart certain molecules that hold nickel, releasing atoms that glow at the wavelengths our instruments monitor. Grain size can matter as well. Smaller grains heat faster and release different species than larger chunks. If the surface accumulates a particular mix through long exposure to interstellar radiation, the release can tilt toward nickel without demanding anything exotic. A competing view suggests that nickel could arise from deeper materials that contain compounds with higher volatility than their iron-rich cousins. If nickel-bearing carbonyls formed in the original environment, sunlight near, current distances could unbind them, while iron remains trapped in less volatile phases. Evidence is limited, but one inference is that the relative absence of iron in the spectrum says more about the pathways of liberation than about the absolute bulk composition. In other words, the ingredients may still be present in familiar ratios deep inside, while the kitchen vent is selecting for nickel during this season of heating. Now move to the volatiles, where the loudest singer is carbon dioxide. Many comets announce water as the headline, with carbon dioxide and carbon monoxide providing harmony in the background. Our visitor flips that arrangement in multiple observations, with carbon dioxide providing a strong fraction of the gas flow. That matters for dynamics, because carbon dioxide can escape through more widespread pores and fractures, especially on a surface that has been compacted and processed by time. Broad release produces a push that is more evenly distributed and therefore more likely to cancel itself when averaged over a rotation. A carbon dioxide-rich coma can look lively, while the orbit remains stubbornly close to gravity only. If water jets are sparse or weak, the strong asymmetric kicks that drive clear, non-gravitational terms may simply not exist. This is where chemistry meets geometry. Imagine a sphere with dozens of tiny vents that breathe together. Each vent is a straw that blows outward with similar strength. The body turns, sunlight shifts, but the field of breath remains balanced in the round. Any single moment captures little asymmetry. Over many moments, the vector sum trends towards zero. The coma brightens, the tail responds to radiation pressure, spectral lines rise in step with the clock of heliocentric distance, yet the dynamical fit refuses to drift. The system looks active because it is active. It looks quiet in the orbit because the activity is everywhere rather than somewhere. What about the missing iron? The simplest test is to watch how the nickel lines and the carbon dioxide band evolve together with distance. If both rise smoothly with heating, that supports the case for natural release mechanisms. If iron sneaks above the floor at closer ranges, that would suggest that the early absence was a threshold effect, not a statement about true scarcity. Analysts can also look for subtle companions to nickel that would be expected in engineered erosion, then check whether those companions exist. So far, there is no public report of non-natural pairings. A minority view holds that nickel-rich traces could echo wear from high-temperature alloys. The idea is intriguing as a materials thought experiment. It remains a minority view because simpler pathways exist, and because no independent signature of technology has appeared. The carbon dioxide dominance invites another practical step. Modelers can simulate a vent field that favors carbon dioxide release over water release, apply a reasonable rotation state, then compute the expected non-gravitational term. If that term sits below current detection limits, the chemistry provides a clean natural bridge between spectacle and silence. If the model predicts a term that should already be visible, then composition alone is not enough, and mass or measurement limits must join the explanation. In either case, chemistry is no longer a curiosity. It becomes a knob that turns the thrust map towards symmetry. At this point, a single sentence reorientation helps. We are accumulating reasons why activity can be bright yet dynamically quiet, and unusual chemistry may be the most direct way to flatten the push without hiding the breath. The ledger closes with a practical tension. Spectra tell us what leaves the surface. Orbits tell us how hard that leaving shoves the body. When those stories disagree, we learn. Here they disagree politely. The coma is loud where carbon dioxide speaks. The orbit is soft where water jets would have shouted. That polite, the disagreement now points toward the other big lever in the equation, the mass that sits inside the glow. If the body is heavier than we think, the same chemical chorus could be singing to a stone that barely moves. The next chapter turns to that possibility, and to the way a single equation can turn missing acceleration into a lower bound on what the nucleus might weigh. There is a simple bridge between force and motion that every physics student learns. Force equals mass times acceleration. If you can estimate the push and you cannot find the acceleration, the algebra points to mass. Outgassing supplies the push. Spectra tell us that molecules are leaving, and models turn line strengths into rough production rates and outflow speeds. The orbit fit provides the other side of the equation. It says the acceleration is smaller than a given limit. Put these together, and you can compute a lower bound on the mass of the body that sits inside the glow. The answer is not a single number. It is a range that depends on how optimistic or conservative you are about the gas flow. Even so, the range can be large enough to feel like a surprise. Imagine pushing a canoe away from a dock. You feel the canoe slide back under your hands. Try the same shove on a moored barge. Your arms feel the effort, yet the barge dismisses your strength. Comets are closer to canoes. They are small, they respond to modest thrust, they advertise their changes to patient observers. If our visitor acts like a barge, the implication is that the nucleus could be much heavier than its brightness suggests. A small mountain wears a fuzzy cloak of light and refuses to twitch. That picture explains silence in the residuals without invoking special tricks. It roots the paradox in inertia. The fog in the picture is real. You do not measure mass directly from Earth unless a companion probes the gravity field. You infer mass by combining uncertain pieces. Gas production rates carry errors from calibration, from slit losses in spectrographs, and from assumptions about temperature and velocity. The acceleration limit carries errors from crowded star fields, from coma contamination of centroids, and from gaps in cadence. The uncertainty from each side multiplies when you divide one by the other. That is why mass bounds derived from outgassing are framed as lower limits with large error bars, not as declarations. Brightness makes the fog thicker. Telescopes see a point that is not a point, a nucleus wrapped in its own exhaust. The unresolved core borrows light from the coma and returns it as a single blob. The blob can mimic a larger or smaller solid depending on how the light is modeled. If the nucleus is darker than assumed, it must be larger to reflect the same amount of light. If it is brighter than assumed, it can be smaller. Those possibilities feed directly into how bold you feel when you translate an acceleration limit into a mass flaw. The same coma can hide a compact giant or a modest stone with a sparkling coat. Until a camera resolves the nucleus or a thermal curve breaks the degeneracy, mass remains a number behind frosted glass. One possibility is that the heavy answer is true. If the nucleus weighs far more than most comets we have studied, the same outflow that would move a smaller body would barely register here. The composition would still speak loudly in the spectrum, the dust would still unfurl into a classic tale, the visual story would match the images we already have. The dynamical story would stay quiet because inertia wins. This explanation has virtues. It is conservative. It accepts what the data say about activity and about the lack of a strong acceleration, and it reconciles them through a property that is allowed to vary widely, in nature, total mass. A competing view suggests that mass alone is doing too much work in this picture. Large comets have been measured to show non-gravitational effects, even if small. If our lower limit on mass climbs into the realm where the expected acceleration should still be visible, then symmetry must join the explanation. Evidence is limited, but one inference is that a heavy nucleus combined with a broad field of carbon dioxide vents could suppress the net push into the current noise. In that blend, mass does the damping, and symmetry does the cancelling. Neither needs to be extreme. Together they nudge the expected signal below thresholds that are realistic for the current geometry and cadence. This argument can be tested. The most direct path is to resolve the nucleus, or to constrain its size through thermal emission. A resolved core sets a physical diameter. A thermal model that separates warm dust from a warm surface tightens the allowable range for reflectivity. Either way, the mass estimate sharpens. Another path is to pin down the gas production with repeated measurements at different distances. If the outflow rises strongly while the residuals remain flat, the mass floor rises with it. If the residuals begin to curve in step with the chemistry, the symmetry blend becomes the favorite. In both paths, more data trade fog for contour. There is a quiet lesson in intellectual posture here. The mountain in the fog is not a dramatic twist. It is a patient reading of the chalkboard. When acceleration refuses to appear, inertia steps forward. That step does not end the story. It sets a stage for the next measurement, and for the next question. What size hides inside the glow? How reflective is the skin? How fast does the core turn? Each answer narrows the space where mass can hide, and brings us closer to seeing the traveller as it is rather than as a luminous blur. That is where we go next, into the craft of pulling a solid from a halo. Pretend you are trying to weigh a firefly inside a lantern. The glow overwhelms the insect. You see brightness, not the body. That is what a cometary nucleus looks like from far away, a solid hidden inside its own light. Observers fight this problem with a mixture of optics, timing, and patience. They model the soft halo, they subtract it, they measure what remains, and they repeat the process until the remaining point acts like a stubborn star. Only then do they dare translate brightness into size, and even then they keep one hand on the brake. The first tool is the point spread function. Every telescope blurs a point of light into a small pattern. Stars define that pattern on a good night. If the comet looked like a star, the fit would be easy, but the coma adds a shallow pedestal under the point. Analysts build a model that is a star on a pedestal. They adjust the height and width of that pedestal until the residuals flatten. The height tells how much coma light is mixed with the nucleus. The star-like spike tells how bright the nucleus must be to produce the central pixels. No single fit is sacred. Teams vary the model, compare nights, swap filters, and check that the inferred nucleus brightness stays consistent within errors. Reflectivity enters next. A dark rock and a bright snowball can return the same light to a camera. Albedo is the fraction of sunlight reflected. If the nucleus wears a dark coat, it must be larger to match a given brightness. If it wears a bright coat, it can be smaller. Observers rarely know albedo at first, so they borrow a sensible range from comets studied before. That choice introduces a stretch in the answer. The same measured brightness can imply a smaller bright core or a larger dark one. The stretch is not a flaw, it is an honest account of what the image alone cannot decide. Rotation can help. A spinning nucleus presents changing cross-sections and changing patterns of active patches. The total light can wobble in a repeating rhythm. A clean light curve can reveal a rotation period and a lower bound on how elongated the body might be. It can also hint at how surface features drive activity. If the wobble is small, the body could be more round or the active areas more evenly spread. If the wobble is large, the body could be stretched or the vents clustered on one side. Either way, the curve feeds the size estimate by constraining shape. Thermal glow offers another path. At infrared wavelengths, the surface radiates heat. If a sensor can separate warm dust from a warm skin, the flux can fix a size more tightly than reflected light alone. The logic is that a large surface radiates more than a small one at the same temperature. You still need a model for how sunlight warms and how heat escapes, but the degeneracy is different, and the combined result from visible and infrared data can narrow the possibilities to a healthier band. Some teams watch for natural experiments. When a nucleus passes in front of a field star, the star can fade for a heartbeat. That dip is an occultation. The depth and the duration measure the size of whatever blocked the light. Occultations are rare for small bodies, but when they occur, they are golden because they bypass the issue of albedo and coma. Other teams push resolution with lucky imaging or speckle methods that freeze the blur for short moments. The sharpest frames can sharpen the star like spike and isolate the core a little better. All of this work loops back to our central question. If the nucleus is larger than a naive brightness estimate, then mass climbs and the same jets push less. If the nucleus is smaller but highly reflective, mass falls and the same jets push more, which would argue that symmetry must be remarkable to keep the orbit quiet. Either way, pulling a better size from the glow is not a luxury. It is the lever that can tip the balance between mass-dominated damping and geometry-dominated cancelling. Caution remains the tone. The coma itself can change with time, and the pedestal under the point can grow or shrink with heating. A fit that worked last week can fail this week. The light curve can hide under shot noise when the object is faint. Infrared measurements can be confused by dust that glows warmly in the same band. None of these are dead ends. They are reminders that nature does not hand over a clean lab. You build one from repetition, from cross-checks, and from methods that attack the problem from different sides. The goal is simple. See the traveler rather than its aura. Fix the scale of the core. Anchor the mass with fewer assumptions. When that happens, we will be ready to decide whether inertia alone can explain the silent residuals, or whether we must lean harder on symmetry written by chemistry and shaped by spin. To reach that decision, we also need to examine the culture of method, how scientists keep doors open without letting speculation run the room, and how they prepare clear tests for the windows ahead. Science advances with open hands and tight fingers. You welcome new ideas, then you grip the ones that survive testing. With this object, the community has chosen a posture that looks simple and is quietly demanding. Keep natural explanations in front. Mark speculative branches so that no one confuses them with results. Define predictions before the best observing windows arrive. Publish not only measurements but also the limits that those measurements impose. Limits are fences. They shrink the field where fantasy can wander. The first habit is pre-registering the kinds of signals that would move the debate. A firm non-gravitational term that rises with activity and follows a known dependence on solar distance would favor symmetry over mass, because it says the push is present yet small. A resolved nucleus that sets a large diameter at modest reflectivity would favor mass, because it says inertia rules. An isotopic ratio that matches common comet families would steady the natural reading. An odd ratio would trigger more scrutiny, not a conclusion. These are not slogans. They are yardsticks that observers can hold to the sky during specific weeks. The second habit is independent reduction. Crowded fields and bright comae invite subtle biases. One team models the coma with a certain profile. Another team tries a different profile. They exchange frames. They run blind tests where the input assumptions are hidden. If a small acceleration term appears only in one pipeline, it is a red flag. If it appears in several, confidence grows. This redundancy also covers different instruments and seeing conditions. Filters that favor gas, filters that favor dust, images with short exposures to freeze the blur, spectra with careful sky subtraction. Each view contributes a fragment. Together they form a picture that no single technique can forge alone. The third habit is clarity of language. A paper that says there is no evidence for non-gravitational acceleration is not the same as a paper that says there is none. The first is a statement about data. The second is a claim about nature. The responsible form is the first. Likewise for chemistry. Reports that nickel lines appear while iron lines remain at limits do not license grand claims about engineered alloys. They license a search for natural release pathways. They license time series tests that check whether line strengths follow heating and geometry. Speculation can live beside those steps. It cannot replace them. The fourth habit is shared calendars. Telescopes are scarce. Windows are short. Groups compare schedules so that gaps are minimized, and high-value nights are covered from different longitudes. Spacecraft teams look for off-angle opportunities. Even a few images from a different perch can untangle perspective. Coordination turns a patchwork of visits into a campaign. The target benefits. So does the method. Every success in capturing a clean sequence this season will serve the next interstellar visitor. There is a social habit that matters as much as any instrument. Curiosity thrives when people feel safe to publish careful null results. Upper limits are not glamorous, yet they are essential to this case. They prune parameter space. They keep mass within a believable range. They restrict how asymmetric vents can be. The more honest limits appear in the literature, the less room remains for claims that rely on wishful thinking. Young researchers learn that restraint is a virtue, not a weakness. Viewers learn that uncertainty is information when it is measured well. A single-sentence reorientation keeps our aim sharp. We are holding the paradox between two natural levers, mass and symmetry, and we are preparing tests that allow the sky to choose without us forcing the answer. The open-door strategy does not slow the story. It gives the next act its power. In the coming weeks, heating will climb, geometry will change, and instruments will listen for changes in motion and in light. If a small acceleration term appears and tracks the chemistry, symmetry and rotation will rise as the leading explanation. If the term stays buried while activity peaks, mass will carry more weight. If a nucleus is resolved or a thermal curve tightens size, inertia will step out from the fog. The next chapter lays out those windows. It shows what could be decisive, what could remain ambiguous, and how to read the sky when the clock strikes near perihelion. Calendars can feel like instruments when the right dates arrive. The weeks around late October promise a rise in sunlight that will heat the surface, wake stubborn ices, and amplify spectral lines that have been living near the threshold. This is when small effects are most likely to climb above noise. If a non-gravitational term exists but has been hiding, it may begin to gather in the residuals as the coma brightens and the gas flow strengthens. If symmetry truly rules, the orbit may remain calm even while the scene grows more dramatic. The point of a window like this is not to guarantee answers. The point is to tighten the game until nature must show a preference. Begin with the acceleration test. Observers will spread. Astrometric sessions across longitudes to catch the object at different phase angles and at different times of day and night. The goal is a dense necklace of positions that can reveal a slow bend rather than a scatter. If the fitted solution begins to demand a small term that scales with distance from the sun and that tracks the changing gas output, that would argue for a weak but present push. In that case, symmetry is the favorite. The vents exist, and they cancel most of the time, but not perfectly. If the solution remains content with gravity only even as heating peaks, the mass floor must climb, because the same outflow would be pushing harder against a lighter body. The second test is an attempt to see the core. Resolution can arrive by patience or by geometry. Patience means stacking many short exposures to sharpen the star-like center and peel away a layer of the coma pedestal. Geometry means waiting for moments when the coma thins, or when filters can isolate gaslight that would otherwise swamp the point. Any improvement that reveals a stable central spike across nights can be translated into a better size. Infrared windows are especially valuable here. A thermal flux that rises and falls with distance can set a scale that reflected light alone cannot. Even a loose diameter can collapse a wide range of mass estimates into a band that has meaning. The third test lives inside the spectrum. Carbon dioxide has been loud. Water has been quieter. Nickel lines have stood out while iron has been coy. Near perihelion, the balance can shift. If water begins to join the chorus, narrow jets may appear and slightly unbalance the thrust map. If iron clears the detection floor, the early absence becomes a threshold story instead of a chemistry riddle. Analysts will watch ratios rather than solo lines. If nickel and carbon dioxide rise together in a smooth trend tied to heating, natural release mechanisms gain credibility. If one line shows structured variations that repeat with a period not explained by rotation or geometry, curiosity will spike and teams will attempt to falsify any pattern that smells artificial. A side angle can help every test. Spacecraft at Mars have a chance to image the coma and tail from a different perch during early to mid-October. Even a handful of frames can reveal whether a sunward plume sits on a specific hemisphere or wraps around as a broad veil. That knowledge feeds the dynamical model with a better map of active zones. It also calibrates the coma subtraction that ground-based teams must perform to get clean centroids. These images do not need to be pretty to be powerful. A grainy snapshot with the right geometry can do more than a glamour shot from the wrong angle. Timing matters on the ground as well. As the object rounds the sun, its elongation from Earth can shrink. That means some of the best heating occurs when the sky is bright or when the object sits close to the horizon. Teams will employ instruments that can work in twilight, will choose sites with clear, low horizons, and will plan sequences that trade shutter speed for signal to avoid saturating sensitive detectors. Night after night of marginal gains builds a record that no single perfect night could replace. Decisions are not all or nothing. Each window can move probabilities rather than flip a switch. A small measured acceleration that wobbles in step with gas output would favor symmetry. A flat residual record that spans the warmest weeks would favor mass. A core that resolves into a larger than expected body would favor mass. A core that resists resolution despite brightness would favor symmetry, since the implied size would be small, and the same outflow should then push harder. Shifts in nickel and iron behavior will either settle into natural pathways or will keep a corner of the board open for deeper questions. What happens if the weather does not cooperate, or if glare wins more nights than we hope? The answer is that even incomplete windows can raise or lower fences. A single clear astrometric run in a critical geometry can rule out a class of large accelerations. One clean infrared sequence can cut the size range in half. One spectrum that pushes iron above the line can close a distracting loop. The game rewards persistence more than perfection. These are the weeks when the sky becomes a laboratory with no walls. The object will not slow down for us. Heat will climb, chemistry will react, and motion will either whisper or speak up. Our job is to listen with enough coordination and enough modesty that the data can lead. If we do that, the next chapter can step beyond preparation and ask a broader question. Can objects like this expand the way we search for intelligence, not through messages, but through the honest study of what passes through our neighborhood and how it behaves when the sun touches it? For 70 years, the archetype of the search for intelligence has been a dish listening to the dark. The romance endures. A signal arrives from a distant star. A pattern repeats. A message waits behind the static. That picture is powerful and it should continue. Yet the sky is offering another pathway that is less like a broadcast and more like fieldwork. Objects move through our neighborhood. They carry chemistry and structure. They carry histories carved by heat and time. They do not ask permission to tell their stories. They simply pass, and the question becomes whether we will read what they carry with the same attention we give to radio noise. Begin with a simple proposition. A technology can choose not to shout. A probe can choose to look ordinary. A civilization can choose to leave no beacon at all. If that is true, then waiting for an intentional transmission is a narrow bet. Objects offer a form of evidence that is agnostic about intent. They arrive whether or not anyone wishes to chat. Their motions obey gravity and any small thrusts they possess. Their surfaces release gas and dust according to chemistry. If a visitor behaves in a way that strains natural models, the anomaly does not hide behind a philosophy of silence. It is written into the physics of the encounter. This does not imply that every odd behavior points to design. It implies that the search should widen to include careful study of physical visitors as complementary channels. The method remains the same as for all good science. Define tests that discriminate between natural and engineered. Ask for converging lines of evidence. Insist on repeatable analysis. Treat extraordinary claims as hypotheses that must climb a steep hill. A single object rarely clears that hill. A population can. If dozens of interstellar bodies are studied with the same rigor, and if a subset shows patterns that are profoundly unlikely under known formation paths, then the conversation changes from what if to what now. The appeal of an object-based program is practical as well as philosophical. Spectroscopy reveals the menu of molecules that leave a surface. Astrometry reveals how those molecules push or fail to push. Imaging reveals how dust sheets and plumes evolve with angle and time. None of these require the target to cooperate beyond being present. If the pattern of evidence lines up with natural explanations, we learn about other systems through a form of comparative planetology. If the pattern resists those explanations, the burden of proof rises, yet the path to stronger tests becomes clear. Ask for features that cannot be produced by chemistry and rotation alone. Ask for geometric regularities that persist across seasons. Ask for composition that implies fabrication rather than geology. There is also a timing advantage. Surveys are on the verge of discovering more visitors. A new telescope will take repeated deep images of the southern sky and will likely flag objects similar to the current case at far greater rates. That rise in sample size turns singular debates into statistics. If most interstellar comets behave like our homegrown population, that sets a baseline. Outliers then stand out for attention. If many behave with unusual chemistry or unusual dynamics, the theory must expand. Either way, the search gains clarity. We stop arguing about one traveler and start drawing a map of the country they come from. A single sentence reorientation will keep the thread tight. We are holding a paradox that pits activity against a quiet orbit, and we are widening the search philosophy so that such paradoxes become data points in a larger picture, rather than lonely puzzles. A responsible narrative must remember that people hear the word alien and skip to the end. The right tone keeps the wonder but bars the door to certainty. Say clearly that the safest reading today is natural. Say clearly that 2 of the 3 well-studied interstellar visitors have behaved in ways that stretch intuition in opposite directions. Keep both thoughts in view. The honest position is that nature is more various than our textbooks, and that our instruments are finally good enough to watch that variety in real time. Hold to that, and the search becomes less about answers on demand, and more about building a humane patience that can endure long nulls and rare surprises. The next chapter will respect that posture while stepping into a controlled speculative corridor. People will ask whether active stabilization could hide in plain sight. The question deserves a response that explains what engineered control would look like, what signs it would leave, and how the current object fails to meet that bar. Curiosity can walk that corridor without claiming a revelation. The sky will still have the last word. There is a question that arrives as soon as the numbers refuse to bend. Could an active object cancel its own push on purpose? Engineers call the family of tricks attitude and station keeping. A spacecraft can fire tiny thrusters in patterns that quiet tugs from sunlight or outgassing. It can spin reaction wheels to tilt its face to the sun while keeping its path steady. Human machines do this around Earth and around distant worlds. If a probe wanted to look like a natural comet, it could vent in ways that mimic geology while hiding any net drift. One possibility is a ring of small cold gas jets that respond to sensors and cancel asymmetries as they arise. Another possibility is a surface that changes how it warms so that hotspots move to neutralize recoil. These ideas live in the toolkits of mission designers. They do not require magic. They do require design. What would such control look like in the data? It would not look like a bold signature. Careful control leaves only footprints at the level of timing and subtle correlation. A competing view suggests we would see a non-gravitational term that tracks a schedule rather than solar distance. For example, a tiny correction at regular intervals that does not match rotation or season. It remains uncertain whether such micro-patterns could be teased from current astrometry, given the noise and cadence. Another clue would be an image of the nucleus that reveals geometry hard to reconcile with fracture and pit formation. Clean angles, repeating arrays, or reflective panels would raise eyebrows in any analysis meeting. So far, nothing like that exists in the public record for this object. The core is not resolved, and the coma covers any fine structure. Materials could whisper as well. Evidence is limited, but one inference is that a technology that operates at high temperature might shed a distinctive mix of atoms. A minority view holds that nickel-rich traces could echo wear from advanced alloys. That is a clever idea, yet it comes with hurdles. The spectral trend must separate from natural pathways, and it must pair with other lines that a furnace of geology would not produce. The lines we have are well known in comets, and the ratios can be explained by selection, effects in what leaves the surface. Without a companion signature that demands artifice, chemistry stays inside the house of nature. There is a deeper reason to be slow here. Any device that cancels outgassing recoil must manage energy and bookkeeping. It must know where thrust is and where it is not. It must spend propellant or modulate vents in real time. That behavior would tie itself to the rotation of the body or to the rise and fall of sunlight in some detectable way. If the correction is driven by sensors and firmware, the adjustments might occur at repeating phases that do not match the simple physics of heating. To find that pattern, observers would need a dense calendar of positions and spectra, all locked to a common clock that follows the candidate period. That work is possible. It demands a level of cadence that few campaigns can sustain at small elongations under crowded skies. For the moment, the better use of imagination is as a test generator. If device-level control is really at work, then a strong increase in activity near perihelion should not produce a proportional increase in measured drift. The cancelling system would scale to match. If nature is at work, an increase that favours asymmetric vents should bring a small but measurable response in the residuals. Either outcome is interesting. A flat record through peak heating would press the mass floor up and would sustain the idea that symmetry rules. A small term that grows and fades with the chemistry would argue that we are seeing natural recoil that had been below our threshold. There is also the question of motive that belongs to story rather than to data, yet it has a scientific use. Ask what a reconnaissance probe would try to learn. Ask what geometry would serve that purpose. Ask whether the present trajectory and the present angles maximize any view of planets or fields of satellites. If the answers do not stand out from natural orbital mechanics, the burden falls back on physics. A trajectory that refuses special pleading is a reason to prefer geology over design. Curiosity does not require closure. It asks for clear gates. One gate is an image of the nucleus that reveals the shape of a rock rather than a machine. Another gate is a time series that shows motion that correlates with sunlight and rotation rather than with arbitrary schedules. Another gate is a chemical record that rises with heat and shows no strange companions. If we pass these gates, control in plain sight becomes an elegant concept that the sky did not need. If we fail them, the field will change. For now, the known tools of nature are sufficient to explain a quiet orbit in the presence of a loud coma. The tests ahead will tell us whether those tools are enough in practice or whether something more organized is breathing in the dark. Begin with a quiet rule. A signature points to design only when natural stories fail in converging ways. One curious plot or one bright line is never enough. The case becomes persuasive when different instruments, different teams, and different kinds of data point toward the same unnatural pattern. That principle keeps the conversation honest. It also gives us a checklist of evidence that would move the present object from mystery toward intent. First, consider motion that refuses to follow sunlight. Most non-gravitational effects breathe with heat. The signal grows as the object approaches the sunday. The signal relaxes as it recedes. Rotation modulates that rise and fall with a period tied to the spin. A compelling signature would be a residual pattern that repeats on a schedule that ignores both distance and rotation. Imagine tiny nudges that occur at nearly equal intervals over weeks, with phases that drift in and out of daylight without caring about thermal conditions. A clock that lives outside the star would be suspicious. Observers would test this by constructing a clean timeline of positions with precise timestamps, then searching for periodicities that line up with nothing in the geometry. If such a clock survived independent reductions, and remain stable through changing viewing angles, it would demand attention. Second, look for shapes that nature rarely builds. Comet surfaces are rough, pitted, and layered. They break along irregular planes. They slump and crack. A decisive image of a nucleus with clean angles, repeating arrays, or large, smooth panels would tilt the balance toward artifice. At present, we do not have such resolution. The coma hides the core. Yet this is the kind of one-shot measurement that can end a debate. A single frame that reveals geometry outside brittle ice and dust would outrank 100 marginal fits. Until that day, size and albedo remain the practical targets, but the door stays open in case a lucky view arrives from an oblique spacecraft perch. Third, listen to chemistry for codes that geology does not write. Natural comae carry families of lines that rise with heating and with changing phase angle. Ratios have ranges that reflect where the object formed and how it was processed. A signature of intent would look like structured modulation that repeats with mathematical order. Prime intervals in the timing of line strength changes. Irrational ratios that remain stable through geometry changes. Cross-species beats that track each other with precision beyond what simple release pathways can produce. Spectroscopy would need to show that these patterns cannot be explained by rotation, by geometry, or by gas dynamics. Analysts would also require that independent instruments at different sites recover the same structure after normalizing for cadence and noise. Fourth, ask for companions across methods. A small periodic nudge in the residuals that matches a pattern in the spectrum would be far more interesting than either alone. Add an image that reveals a stable preferred orientation which is not tied to sunlight, and the case becomes stronger again. The weight arrives not from any single surprise but from the stack. Each layer strips away a natural escape route until few are left. Now place these signatures beside the data we have. There is no stable off-solar clock in public astrometry. Residuals do not show a coherent schedule that survives the crowding of the field. There is no resolved image of the nucleus that reveals non-natural geometry. The spectrum shows nickel lines above iron at times, and a strong carbon dioxide presence, but the temporal behavior can be explained by release pathways that nature already uses. Where periodicities exist, they can be tied to rotation or to changes in phase angle. Where oddities appear, they soften with better signal and with longer arcs. There is a softer class of signs that would still be suggestive if found, a non-gravitational term that flips sign at periods not tied to spin, a persistent alignment of the tail plane with a reference frame that ignores the ecliptic, a set of micro-outbursts that recur at equal intervals across many rotations. None of these are present as robust results. Even if one appeared, it would need to survive the same gauntlet of independent checks before it could be called a candidate signature. A single-sentence reorientation will keep us grounded. We are testing a paradox with natural levers first, and any claim of design must vault a much higher bar built from motion, shapes, and chemistry that refuse to act like geology. These criteria are not barriers to wonder. They are the path by which wonder turns into knowledge. By writing down what would count ahead of time, we protect the story from overreach and protect the data from wishful reading. If the sky wishes to speak in the language of intent, these are the letters we will watch for. If it speaks in the language of ice and light and time, these same tests will resolve the present puzzle into a richer understanding of how different worlds breathe. Either outcome is a win for curiosity, either outcome honors the simple rule that extraordinary claims should earn their way through evidence, not through mood. The first time the nickel lines rose above the forest of wavelengths, the result felt like a whisper from a workshop. Nickel often travels with iron in comet comae. The two metals are born in similar furnaces and wander through planetary materials as partners more often than not. Here the partner hid at the floor of detection, while nickel stood in modest relief. That contrast pulled eyes back to the spectra night after night. Was iron truly scarce, or was it simply sleeping below the threshold while nickel found an easier exit path? The answer matters because metals are less prone to the quick chemistry of lighter molecules. Their appearance tends to trace how grains are processed and how deeper surfaces are weathered by long exposure to light and charged particles. Begin with the simplest route. Sunlight breaks bonds. In some materials that contain nickel, solar ultraviolet energy can liberate neutral atoms at lower temperatures than those that free iron. Laboratory studies of carbonyl compounds point in that direction. In a dusty environment, small grains heat quickly and cool quickly. If the surface population has been sifted by countless thermal cycles and by micrometeor impacts, the outermost grains can tilt towards sizes and compositions that favor nickel release. In that case, the spectrum would not be a window into the deep core. It would be a snapshot of a thin veneer. The remedy is time. If nickel is riding a skin effect, its signal should rise first, then level off as the shallow layer is depleted, while iron climbs more slowly and eventually joins the lines as deeper material comes into play near peak heating. Another natural route involves transport rather than composition. Imagine that iron atoms are released at rates comparable to nickel, but are then trapped more efficiently in larger grains or in compounds that do not emit at the observed wavelengths under current conditions. The instrument sees what light allows it to see. A line that is shy near the noise floor can look missing even when it is not. The cure is to watch the same region of the spectrum with increased sensitivity and to push for measurements at multiple heliocentric distances. If iron appears as the object moves closer to the sun, the early silence was a selection effect. A minority view holds that the nickel result hints at wear from engineered alloys. It remains a minority view because such a claim requires companion lines that are difficult to produce through weathered geology. For example, certain alloy wear would be expected to shed specific combinations of trace elements or to show isotopic fractions outside natural ranges. No such companions appear in the public record. Where pairs are expected by chemistry, the observed ratios follow curves that rise with distance and heating in a way that fits non-engineered release. That does not hand us proof, it hands us a stable interpretation. Nickel can shine while iron hides if the cosmos chooses grain sizes and bond energies that favor one exit door over another. Carbon dioxide sits nearby in this story. This object breathes a lot of it. Carbon dioxide can lift fine dust with less dependence on narrow jets, and it can scour broad regions. If a large area exhales together, nickel-bearing grains can be lofted from many sites at once. That would amplify the nickel lines without creating a strong directional push. The mechanism helps the dynamical puzzle as well as the chemical one. A broad field of vents cancels momentum transfer, while filling the coma with metal atoms and molecules that ride the flow. In that setting, iron remains quiet if the surface has not yet reached the temperature regime where the relevant bonds fail. To test these ideas, time is the microscope. Observers can construct a clean timeline of nickel intensity relative to nearby continuum and place that curve next to carbon dioxide and cyanide production rates. If all three rise together in a smooth fashion tied to solar distance and phase angle, chemistry holds center stage. If nickel shows bursts that repeat with a period that is not tied to rotation or geometry, curiosity will spike and teams will try to break the pattern with better cadence and stricter corrections. Analysts can also separate measurements by aperture size, since a larger extraction window includes more of the extended coma. If the nickel-to-iron contrast changes with aperture, that would hint at different lifetimes or transport paths for the two species. There is also a spatial clue that can be sought with high-resolution instruments. If nickel emission peaks along arcs that match dust features while iron remains diffuse or invisible, the grain-driven picture gains power. If both metals concentrate around discrete jets, while the net non-gravitational term stays small, the symmetry of vent layout becomes more compelling. Either map serves the larger story. Both help decide whether chemistry alone can explain a bright metal signature without a strong push in the orbit. Nickel without iron is a phrase that invites drama. The responsible version of that drama is patience. So far, the line behavior can be explained by release pathways that favor nickel under present conditions. As heating grows, iron has every chance to join. If it does, a temporary imbalance becomes a seasonal effect. If it does not, the persistence of the contrast will require deeper thinking about the surface history of this traveler. In both outcomes, we learn how interstellar weather writes itself into spectra, and how metals can act as tracers for processes that shape thrust without announcing themselves as force. The next step uses that timing discipline to see whether trends through weeks can reveal the quiet mechanisms that keep the orbit close to gravity only, even while the coma sings. Time is the magnifying glass that astronomy reaches for when resolution fails. A single snapshot can be a beautiful lie. A sequence, even a modest one, can expose a rhythm that turns confusion into structure. Our visitor rewards that patience. As sunlight climbs and the object sweeps along its path, line strengths rise, tail shapes rearrange, and the balance between gas and dust shifts in ways that can be measured against a clock. If a mechanism has been hiding, its footprint should appear in how those curves change, not on a day, but across many. Start with the volatiles. Carbon dioxide has carried the song so far. If symmetry is the main reason the orbit stays calm, carbon dioxide should continue to dominate, and its production rate should scale with heliocentric distance in a smooth way. The curve might steepen near perihelion, then relax as the object recedes. Water can join as heating deepens. If water remains a supporting voice, the thrust field likely stays broad, and the residuals will remain quiet or only whisper. If water surges and does so from a few privileged vents, that should ripple into a slight but coherent change in the orbit solution. In that case, we would expect a small non-gravitational term to appear just as the waterlines brighten and to soften when they fade. Now set the metals on the same timeline. Nickel lines that rise with carbon dioxide and cyanide argue for a shared driver in sunlight and surface texture. They also argue against abrupt processes that would imply engineered control. Iron climbing out of the noise as the object warms is the simplest outcome. That would turn a puzzling contrast into a narrative about thresholds. If iron remains elusive while nickel grows, the path tightens. Analysts can plot nickel to continuum against phase angle and look for divergence from the trends that gas lines follow. A divergence points to grain physics. A convergence points to common release. Rotation enters like a second hand on the same clock. If the body spins with a period of hours, that spin can reveal itself in the rise and fall of specific features, even if the nucleus is unresolved. Small modulations in brightness, small swings in the shape of the inner coma, small periodic changes in gas ratios, all can be folded at candidate periods to test whether a single rhythm drives them. When a period fits, it offers a map. The face that heats at hour 0 will be different from the face that heats at hour 6. Vents that sit on the morning limb can breathe differently than those at local noon. A rotation solution that favors many active longitudes supports symmetry. A solution that points to a few strong longitudes asks the orbit to respond. Phase angle is the quiet partner in these plots. The same amount of dust can look very different when the sun, the object, and the observer move into new alignments. Anti-tail episodes teach that lesson in a dramatic way. Time series analysis that ignores phase will paint false patterns on honest data. The fix is simple and fussy. Every measurement must be tagged with geometry. Every trend must be corrected for viewing angle. When that is done, what looked like a change in physics will dissolve into a change in perspective. What remains are the true seasonal curves that track heating. Cadence matters as much as any model. Gaps eat signals. Weather and glare create gaps. Teams who share schedules can braid their nights into a tighter rope. A run of modest frames across a week can beat a single night of perfect seeing because it reveals slack that a still image hides. In the same spirit, small telescopes that can watch often can anchor the timing, while larger instruments visit less frequently for precision. The union of sometimes and sharpness is stronger than either alone. What would success look like? It would look like a set of curves that agree in their broad strokes. Carbon dioxide climbs and falls with distance. Water may rise late but stays modest. Nickel tracks the overall, breath with a tilt that time can explain. Residuals remain small, yet a barely measurable push appears when water peaks, then relaxes, which would close the loop from chemistry to dynamics. Or it would look like a flat dynamical record through the hottest days, while all the lines swell. That outcome would push the mass floor higher and would make symmetry the quiet sovereign of this case. A single sentence reorientation can mark where we stand. We are using time to test whether composition and rotation can keep a live coma from moving the orbit in a measurable way, and we are preparing to judge the result by whether subtle curves align. Statistics will one day take over when a new survey fills the archive with dozens of visitors like this. Until then, time is the microscope we have. It does not erase uncertainty, it compresses it. It turns weeks into a lens that can reveal whether nature is balancing her forces across a broad surface, or whether inertia is shouldering the work. With those possibilities framed by trends rather than guesses, we can now widen our view to ask how a flood of discoveries will change what counts as strange in the first place. One object can seduce us into arguments about exceptions. Many objects change the conversation into statistics. The coming survey of the southern sky promises to move us from anecdotes to patterns by photographing vast swaths of space again and again with a cadence that turns the heavens into a time-lapse film. Every 3 nights is a heartbeat. Faint movers pop out of the star fields as threads instead of dots. Tracks link across weeks. Alerts go out in minutes. That flood of motion is the context our current visitor has lacked, a population against which its quirks can be measured without drama. Think first about discovery bias. Until now, we have noticed interstellar bodies only when they were bright, well-placed, and lucky. That means our sample is small and skewed. A deeper, faster survey reduces that skew. It finds the timid as well as the bold, the dim as well as the flashy. The result will be a library of paths and light curves that include 100 quiet travelers for every loud one. In that library, we can ask, how often do high carbon dioxide comet appear? How often do nickel lines rise without iron early on? How often do non-gravitational terms stay near limits despite visible activity? If the answer to any of those questions is often, then strangeness becomes a category rather than a plot twist. If the answer is rare, then our present case stays special, and special cases invite closer scrutiny. The power of many reaches beyond discovery. Cadence is currency. With frequent revisits, even modest telescopes can build dense necklaces of positions that improve orbit fits by force of numbers. The residuals that look like fuzz across a handful of nights resolve into shapes when you have hundreds of points. Small periodicities that were lost in gaps show their faces. Seasonal curves become smooth enough to compare across objects. That is how you calibrate what a typical carbon dioxide-dominated comet looks like at 1.5 astronomical units, and how you spot the one that refuses to behave. A broad sample enables controlled comparisons. Match objects by distance from the sun, by phase angle, by brightness, and by apparent activity, then stack their measured non-gravitational terms. If most show a small positive drift at a given geometry and chemistry, while a few do not, the outliers draw circles around themselves. Then the question sharpens, do those outliers share a common rotation period? Do they cluster in a region of sky where background crowding is worst? Do they share nickel to iron behavior? These are not idle questions. They are the bread and butter of inference when individual cases are murky. The survey will not act alone. Its alert stream will feed a network of spectrographs and high-resolution images that can swing to a target within hours. That coordination turns a discovery into a campaign. A typical night might begin with a fresh detection, pivot to a spectrum for chemistry, then to time-resolved imaging for light curves, then to a late session of astrometry that grabs a few more precise positions near dawn. Repeat that rhythm across continents, and you get coverage that no single observatory could provide. Our current paradox would have been easier to weigh under that regime. The next will be, there is a deeper change that statistics bring. They allow us to separate personality from physics. A single object invites stories about singular origins and exotic histories. 100 reveal the boundaries of what nature does with regularity. If high carbon dioxide comet commonly suppress net thrust, models will adapt and textbooks will gain a new page. If nickel without iron is a frequent seasonal effect, rather than a rare chemistry trick, the line will lose its mystery and gain its place as a tracer for surface processing. If a handful of objects consistently refuse to show non-gravitational effects across well-sampled arcs while sharing other uncommon traits, then those handful move to the front of the line for special attention, perhaps even for a fast spacecraft intercept. A single-sentence reorientation holds the thread. We are trying to decide whether mass and symmetry can explain a quiet orbit under loud activity, and a larger population will tell us if this balance is a one-off or a pattern. The Rubin era also democratizes vigilance. Citizen scientists and small observatories will receive streams of candidates that they can patrol with pride. A small scope cannot outgun a giant mirror, but it can contribute nightly timing that fills gaps. Students can cut their teeth on real-time anomalies, and learn to weigh speculation against method in the same rhythm that professionals follow. The culture shifts from chasing media storms to maintaining a watch that makes storms unnecessary. When something truly odd appears, the scaffolding to study it is already standing. For the present object, the promise of many does not erase the urgency of one. Its clock is still running. Its chemistry will still crest and fade. What the survey will change is our confidence about what we are seeing. The next visitors will arrive into a world where the default maps are better, the biases are smaller, and the pipelines have been trained on synthetic edge cases to avoid common traps. In that world, tension and wonder still thrive, but the guardrails are higher. That is the point of progress. Keep the thrill, lose the confusion. With that ethic in mind, we can return from the population to the person and ask how to hold an entertaining mystery in public without teaching bad habits. Wonder is the hook. Guardrails are the craft. Wonder is the fuel of science television, but it can also be the smoke that hides the controls. Tell a story about a mysterious visitor too loosely, and you train the audience to crave leaps instead of steps. Tell it too stiffly, and you drain the color from a genuine frontier. The craft is to keep the heart rate up while the logic stays seated. That means describing anomalies with vivid language, then fitting that language into a frame that rewards patience. With this object, the balance is not a slogan. It is a set of habits that show up in every scene we stage and every line we write. Begin by anchoring the stakes in curiosity rather than fear. The orbit is safe with wide margins between the traveler and Earth. Say it simply, no hazard to the public. Confidence rises when people hear that sentence early and often. Safety cleared, move the urgency onto knowledge. We have a brief window when heating will clarify chemistry and geometry. Clocks can drive a story without terrifying anyone. A bright countdown graphic, a soft chime on approaching dates, a map that shows the path across the inner system. These are tools that nudge viewers to care about a schedule, while understanding why the schedule matters. Next, keep the axis of known and unknown in view at all times. When you show a plume, say what plumes usually mean. When you show a tail, say why an anti-tail can appear, and why it does not overturn physics. When you say non-gravitational acceleration, pause just long enough to remind the audience that it is a measured effect in many comets, and that its absence here is the reason for the story, not proof of anything wild. One-sentence reminders protect the thread. They also make the speculative moments feel earned when they arrive. Speculation belongs in labeled rooms. One possibility is deliberate stabilization, and we explored how such control could look if it existed. A competing view suggests engineered wear patterns could mimic unusual metals, and we explained why natural release pathways remain a better fit. It remains uncertain whether mass or symmetry dominates the quiet orbit. Evidence is limited, but one inference is that carbon dioxide-rich venting distributes thrust in ways that cancel more than they push. These phrases are more than manners, they are boundary ropes. They tell the audience that the show is entertaining first, but also honest about where evidence ends. Show it, do not only tell it. Visuals can carry restraint without killing momentum. A residuals plot that refuses to bend can be beautiful if you treat it like a slow reveal. Layer gravity only in chalk white, layer the measurements in faint gold. Let the two sit almost on top of each other while an understated score hums. The audience will feel the tension of almost. A spectral timeline can carry the same charge. Nickel brightens while iron rests at the floor. Carbon dioxide rises early. Water follows late. The lines climb like city lights turning on at dusk. You are not dumping statistics. You are staging a living graph. Give the audience tools to resist noise. Explain what an upper limit means in a single clean sentence. An upper limit is a fence, not a blank. Explain why crowded star fields can hide a small effect. Show a cropped frame filled with stars, then the same frame with the object blinked in and out. People will grasp the difficulty, and they will forgive ambiguity that comes from honest limits. Teach them that a null trend across a hot week can be more decisive than a single dramatic image that sits out of context. Finally, model humility. Admit where the show compresses time or simplifies math. Promise that if a small non-gravitational term appears near perihelion, future episodes will update the conclusion. Invite viewers to watch the dates with you, to check observatory feeds, to compare their notes with the checklists we have written together. Treat them like partners. Wonder grows when people feel included in the method, not only in the mood. A single sentence reorientation keeps our course. We are holding a paradox between a loud coma and a quiet orbit, and the story stays thrilling when we couple clear tests with vivid scenes and mark speculation as a guest, not a host. The next act tightens the two leading natural explanations and places them on a single stage. If symmetry writes the quiet path, what evidence will mark it? If mass is the anchor, how large must the core be to keep the orbit still under rising breath? We will set those arguments side by side, then carry them forward into the weeks when the sun presses closest. Lay out the contenders cleanly. On one side sits symmetry, the idea that many small vents breathe together and cancel their recoil most of the time. On the other side sits mass, the idea that a heavy nucleus absorbs the same push with barely a twitch. Both are natural, both are testable, both can be true in part. The question is which explanation carries more of the load for this object, and which predictions will break the tie as heating climbs. Start with symmetry. Imagine a sphere pocked with tiny pores that exhale carbon dioxide across many latitudes and longitudes. Carbon dioxide is good at this broad style of release, especially on a crust that has been seasoned by time. Each pore is a straw. Each straw produces a small thrust vector. The body rotates, sunlight sweeps across the face, and the vectors add and subtract with every hour. If the map of pores is rich and fairly uniform, the net push tends towards zero when averaged over many rotations. In that picture, the coma is lively because the total mass flow can be large, yet the orbit remains quiet because the forces cancel. Symmetry does not need to be perfect. It only needs to be good enough that the remaining imbalance hides within current noise. Symmetry makes clear predictions. A small non-gravitational term may appear near perihelion, then wobble in step with measured gas production, but it should remain small. The term should show a dependence on distance from the sun that matches the chemistry. Water lines, if they rise, may introduce a brief bump, since water favors more focused vents. That bump should arrive and depart with the water. Nickel lines should rise with the overall breath, not in an independent rhythm. Light curves may reveal a modest rotation period, with small photometric amplitudes that imply a shape close to round, or at least not extremely elongated. When observers fold spectra and residuals at candidate spin periods, the patterns should look like shallow breathing rather than like a metronome. Now, turn to mass. Think of a compact core, darker than average, larger than naive brightness suggests. The same jets that would move a modest nucleus create a whisper of acceleration against this inertia. The residuals stay flat because momentum transfer per kilogram is small. Mass also makes predictions. If mass dominates, then even as gas output rises sharply near perihelion, the orbit solution should remain content with gravity only, or should accept only a very small additional term. Attempts to resolve the nucleus should favor a larger diameter for any reasonable albedo. Thermal measurements that separate dust from a warm surface should point to a sizable radiating area. If rotation is detected, the photometric amplitude might be small, not only because the shape is round, but also because a larger body smooths the contrast from surface features. In the spectrum, water can still rise, nickel can still glow, but their peaks should fail to pull a measurable bend in the fit. Which pathway fits the record so far? We see a carbon dioxide-rich coma that lights up early. We see nickel above iron in some epochs. We see plumes and tail evolution that confirm activity. We do not see a strong non-gravitational term. Those facts line up comfortably with symmetry. They also leave room for mass. The deciding weight rests on how the numbers move in the hottest weeks, and on whether anyone manages to anchor the size of the core more firmly than before. If a nucleus resolves larger than expected, the mass story will stride forward. If a small non-gravitational term appears and tracks the chemistry, symmetry will step into the lead. If both occur, the blend wins, which is likely in a messy universe. The two camps are not enemies, they are lenses that sharpen each other. A model that assumes symmetry can be overlaid on the time series to see whether water-driven patches disturb the calm. A mass-forward model can be challenged by pushing lower bounds on gas production. If a given outflow and a given non-detection imply an absurdly heavy core, the assumption must bend. The best work will try to fit both at once. Build a map of vents that matches the spectrum. Add a rotation state that fits any photometric wobble. Place that on a nucleus with a diameter set by thermal and reflected light together. Then ask the orbit to respond. If the simulated residuals fall below the actual residuals and follow the same flat line, the case is strong. If they do not, something is missing. There is a reason to keep drama in check while we argue the balance. Both explanations teach us something about formation beyond our system. A symmetric carbon dioxide field suggests a surface that is porous and seasoned, with chemistry that differs from many comets here. A heavy core suggests a history that compressed material into a compact body, or a collisional past that built a rubble pile dense enough to act like a single stone. Either story is worth learning on its own terms. Either story refines how we think about the families of small worlds that emigrate from other suns. The head-to-head does not end in a courtroom verdict. It ends in a lab report written by the sky. As we round the bend toward maximum heating, every line that brightens and every centroid that holds still will push the needle. In the next chapter, we take the tests to their natural venue, the weeks near closest approach. When instruments run hot and the object has its best chance to choose between breath that moves a path and breath that glows without a shove, perihelion is not a single moment. It is a short season where sunlight sharpens every question, surfaces warm, ices cross thresholds, jets that were whispers can become voices. In that season, the object writes its clearest signature into light and motion. If the orbit is going to reveal a small, non-gravitational term, this is when it should rise above the noise. If mass and symmetry are going to keep the path quiet, this is when their partnership must hold under the hardest push. The test is simple to state and hard to pass. Measure the same few things often and with care. Watch the chemistry climb, watch the positions slide, ask if the slide follows the breath. The first measurement is the necklace of positions. Observers plan chains of short visits rather than isolated marathons. A night might deliver a handful of precise centroids at the start of twilight, another handful near midnight, and a final handful near dawn. Spread that rhythm across sites that can work. In bright skies and the chain grows. Each bead carries a timestamp and an uncertainty. When the chain is long enough, modelers try two fits. One assumes gravity only. The other allows a small additional term that varies with distance from the sun in a standard way. If the second fit reduces residuals across many nights and across different instruments, the test returns a positive. If the first fit remains as good, the test stays near zero and mass gains ground. The second measurement is the spectral ladder. Carbon dioxide sits on a lower rung that lights early. Water sits on a higher rung that lights later. Nickel lines live on a side ladder that traces grain physics and surface processing. Near perihelion, all three can change in strength. The question is whether the dynamical record changes in step. If water rises and a small acceleration appears with the same timing, the symmetry story wins points since it says focused vents finally produce a measurable imbalance. If water rises and the orbit remains stoned still within limits, the mass floor climbs, and symmetry can still play a role as a counselor. If nickel climbs without iron yet again, the chemistry puzzle persists, but the dynamical verdict does not depend on that alone. What matters is correlation across the ladders. The third measurement is the light curve. Modest photometric wobble can pin the rotation period and reveal whether active regions repeat on a clock tied to the spin. A rotation solution allows analysts to fold the residuals and the line strengths against the same phase. If the peaks in gas and the tiny shifts in position share a phase, that is natural. If there is no shared phase, that is also natural when symmetry rules. If there is a repeating phase in motion that does not match the spin or the distance, that would be strange. So far, there is no reason to expect such a clock. Perihelion simply offers the best chance to check. A side vantage can add leverage. Instruments at Mars can take sparse images from an angle that separates plumes from perspective tricks. Even a few frames where a sunward veil is seen off to the flank can clarify whether the object breathes from many sites or from a few. That map flows back into orbit models that try to predict a small acceleration. If the predicted term is below detection limits and the data agree, The result is satisfying even if it feels quiet. Not every experiment ends with fireworks. Some end with fences drawn in the right place. Perihelion also brings trouble. Elongations shrink. The object slides closer to the sun in the sky. Backgrounds brighten. Atmospheric paths lengthen near the horizon and add turbulence. Teams counter with short exposures, with careful background modeling, and with filters that isolate strong bands. They accept that some nights will produce frames that serve only as practice. The patience is worth it. There are regimes where one night at a hard angle can rule out an acceleration that would otherwise remain plausible. What would a decisive outcome look like? The strongest case for symmetry would be a small non-gravitational term that grows and then softens in step with carbon dioxide and water, with a phase tied to rotation that never dominates and never vanishes. The strongest case for mass would be a flat dynamical record through the hottest days, paired with spectra that prove abundant gas flow, and with a thermal size that argues for a large core. Either outcome respects the laws we already trust. Either outcome also rewrites a footnote about how interstellar visitors distribute their breath. There is room for surprise. A shallow term might appear for a week, then retreat into the limits. A metal line might jump on one night, then settle into the curve again. These are features, not bugs. Nature is allowed to be twitchy when heated. What matters is the trend that survives the noise. As perihelion passes, the plots will begin to harden into stories. They will not answer every question. They will answer enough to tilt the balance. In the next part, we prepare for the possibility that the silence holds anyway, and we sketch how science moves forward when the best window leaves a riddle intact. Imagine the last plot after perihelion, a clean band of points that refuse to drift in any one direction, a quiet necklace that lays almost exactly on the gravity-only curve. The coma sang, the lines in the spectrum climbed, yet the path stayed calm. If this is the outcome, it is not a defeat. It is a statement about how nature can hide a push when symmetry and inertia share the stage. Science moves forward by tightening the frame around possibilities, and a flat record through the hottest season pulls that frame in by a meaningful amount. The first step is to write down the fence. An upper limit is a tool. It says that any net acceleration must live below a specific number tied to real data. Put that number beside estimates of gas production. The product sets a floor for mass or a ceiling for asymmetry or both. That fence trims the garden of theories. Wild vent maps that produce strong one-sided pushes no longer fit. Low-mass cores that would have twitched under the measured outflow no longer fit. Claims that depend on a hidden engine become harder to defend because the same chemistry under a quiet path needs no extra agent. The paper that publishes such a fence is not a placeholder. It is a cornerstone for every later argument. The second step is to tune the tools. Teams will revisit coma subtraction methods and centroid algorithms with the fresh knowledge that the true signal is small. Synthetic images can be injected with artificial drifts that sit near the new limit to test which pipelines recover them and which do not. A reduction method that swallows a simulated drift needs to be retired or repaired. A method that recovers that drift without ballooning errors earns a larger role in the next campaign. This is how quiet results are, transformed into better practice. The third step is to update models with humility. A dynamical code that uses a single strong jet as its template may need to include dozens of small sources that breathe together. A thermal model that assumes water-driven activity may need to shift its emphasis to carbon dioxide and to porous crusts that leak across wide regions. A community that has favored easy examples will need to widen its training set to include cases that look like this one. That includes building libraries of synthetic visitors, where high carbon dioxide comet produce bright shows with minimal push, then running those through the entire analysis chain to see where biases emerge. In parallel comes the question of action. If flat residuals survive the best window, fast intercept concepts move from thought experiment to serious study. Small spacecraft with modest propulsion and agile cameras could be designed to rendezvous with the next target that shows a similar chemistry and similar dynamical quiet. A flyby would help, a brief escort would change the game. A probe that tastes gas and dust in situ would show whether the broad release we infer from Earth truly exists, and whether small water vents hide under the carbon dioxide chorus. Space agencies and private teams can sketch variants that park in ready orbits, then sprint when a new alert arrives from a survey. Archives become more valuable in this scenario. If silence holds, then detailed records of when it held and under which geometries will matter to every later visitor. Observers should deposit raw frames, reduction scripts, and logs of observing conditions in open repositories so that future teams can rerun the past with better methods. That habit is not a burden. It is a way to amortize effort across years. A student in the next cycle can test a new centroid tool on this object and report whether the limit can be squeezed a notch lower. A small improvement in one number across many cases shifts an entire field. A single sentence reorientation helps keep us steady. We are learning how a loud-coma can leave a quiet orbit, and a confirmed null during maximum heating strengthens mass and symmetry as the prime actors without closing the door to refine tests. Communication also matters when silence survives. The story must tell the public that absence can be meaningful. A montage of rising spectral lines next to a motion plot that refuses to curve can be cinematic if the voiceover explains why that refusal is profound. Make the fence visible on screen. Show the mass floor that rises when the dynamical line stays flat. Explain that a quiet result is how precision earns the right to speculate less and to understand more. Wonder will survive that restraint. In fact, it will grow, because it is anchored. Finally, let silence redefine what counts as interesting. The next time the alert stream announces an interstellar visitor with early carbon dioxide and a shy, non-gravitational term, we will be ready. We will not overpromise. We will not undershoot. We will build a plan that assumes nature enjoys balance, and we will design tests that feel at home in that balance. The riddle will not vanish. It will mature. The field will follow. Progress sometimes hides inside unglamorous upgrades. Before this object, many teams treated coma subtraction as a routine step. After months of wrestling with a bright halo wrapped around a quiet core, coma subtraction moved into the center of the craft. Groups built new kernels that behave well in crowded Sagittarius frames. They validated those kernels on synthetic scenes where faint drifts were injected at known levels. They learned which filters isolate gas light enough to sharpen a centroid and which filters invite dust to blur the answer. The result is a sturdier bridge, from raw pixels to positions that a dynamical fit can trust. Coordination habits improved as well. Observers who once guarded nights like family heirlooms began to braid their calendars on shared sheets, dawn in one longitude handing off to twilight in another. A modest telescope that could not reach deep magnitudes still became a metronome for the light curve, keeping phase honest, while larger mirrors dipped into spectra. Spacecraft teams learned where a handful of off-angle images deliver leverage that ground setups cannot. Even a grainy shot from Mars orbit turned into a useful constraint on where plumes lived and how far they wrapped around a hemisphere. Pipelines felt the pressure and emerged leaner. Astrometric reductions now flag frames, where the centroid shifts when a different coma model is used. Spectroscopy pipelines now staple a geometry card to every line measurement, so that phase effects can be removed before a trend is claimed. Cross-checks evolved into culture. If a small non-gravitational term appears from one group, a second group can rerun the same frames with a different recipe and report whether the signal survives. Limits often replaced claims, and that was a win, because limits are the numbers that future visitors must respect if they hope to be called unusual. The educational ripple is easy to miss and important to note. Students saw senior voices treat upper limits with respect, and that example will travel. They learned to put natural explanations first and to park speculative corridors where they belong, clearly labeled and ready to be closed by better data. They watched how a single sentence can carry guardrails. This is not a threat. This is an opportunity with an expiration date. The show kept its pace without bartering away precision. Instrumentation received a quiet nudge. Infrared programs sketch small upgrades that separate warm dust from warm surface with cleaner kernels. Fast guiding routines improve near the horizon, where twilight and turbulence conspire to smear an object that happens to be in the right place at the wrong time. Designers of compact deep space probes revived, outlines for rapid intercepts that can launch on short notice when the next candidate shows similar chemistry and similar dynamical calm. The lesson from this season is not that answers are scarce. It is that answers arrive for those who have tuned their tools before the window opens. A single sentence reorientation keeps the compass steady. We are learning how to hold a loud coma and a quiet orbit in the same frame, and the methods built for this case will make the next case easier to read. Public storytelling adjusted too. Producers discovered that a residuals plot can be staged like a cliffhanger, and that a clean upper limit can land like a verdict if the audience knows what the fence means. Viewers wrote in to ask for the dates when new spectra would arrive and for the reasons a non-detection would still matter. Curiosity was not diminished by caution, it was guided by it. That change will outlast this object. When the window closes, a field that began with a paradox will keep a portfolio of gains, better kernels, better calendars, better instincts about how carbon dioxide-rich comet can shine without moving the path. The final step is to sit with meaning. Artifact, or oddball, is a catchy headline, but the better question is what this chase adds to our map of how the universe works and how we should look for company within it. That is where we end. Two doors have framed our entire story. Behind the first sits nature, operating at the edge of our expectations. Behind the second sits design, subtle and careful, hiding in plain sight. The safest reading today opens the natural door. The visitor breathes an unusual mix dominated by carbon dioxide. It likely vents from many places at once. It may carry more inertia than its brightness first implied. Together, symmetry and mass can keep the orbit quiet while the coma sings. Nothing in the public record requires another hand on the tiller. That is not a dismissal of wonder. It is wonder, accepting the rules it has, already earned. Why say this aloud? Because words shape how we search next time. If we pretend certainty where evidence is thin, we train ourselves to miss real signatures when they finally appear. If we refuse to hold the gate for speculation, we train ourselves to ignore outliers that can rewrite a page of the book. The middle path is harder and more honest. One possibility is that a small non-gravitational term will still emerge from the hottest weeks, phasing with the chemistry and reminding us that patience bends noise into signal. A competing view suggests that the residuals will remain flat enough that mass must shoulder most of the explanation. It remains uncertain whether any single lever can carry the whole load. Evidence is limited, but one inference is that the blend of broad carbon dioxide release and respectable inertia can reconcile almost everything we have measured. So, why does the artifact door remain in the frame at all? Not because the data point there, they do not. It remains because the universe might one day present a visitor that refuses every natural story with converging stubbornness. If that day comes, we need a checklist written before the mood gets loud, motion that follows a clock no star can wind, shapes that fracture along clean angles, chemistry that encodes ratios no geology can synthesize, and that repeats across instruments that do not share biases. Until such signs appear, we keep that door closed without locking it. We do not mock curiosity. We do not hire it to write the ending. What endures beyond this single case is a wider map of the possible. We now have a richer sense of how an interstellar object can look alive and still keep to gravity's chalk line. We have seen that nickel can rise while iron hesitates, and that the simplest response is to watch longer rather than to declare a mystery solved by a guess. We have practiced telling a story that keeps tension high while respecting the audience enough to mark the speculation clearly. We have built habits that will pay off when surveys begin to flood our inboxes with new tracks and new comet, and new chances to ask the same good questions again. There is also a quiet philosophy tucked inside this chase. Mystery is not a failure of science. It is a compass for it. The border between known and unknown is not a wall to lean on. It is a shoreline to walk. This object lengthened that shoreline. It did so safely, with a path that never threatened Earth. It did so generously, with chemistry and structure that challenged our methods without breaking them. It did so timely, in a season when coordination across instruments and continents could respond. That is a gift. It leaves us with better tools, and with a better script for how to hold excitement and restraint in the same frame. If you are watching the sky with us, you already know how this ends. Not with a trumpet blast, but with a promise. The next visitor will come. The next residuals plot will appear. The next spectrum will draw lines that climb like a city turning on its lights. We will ask the same first question. What is the simplest natural story that fits? We will ask the same second question. What would constitute a signature of design if nature refuses to play by our rules? We will keep both questions near the front of the notebook, and we will keep the word maybe on a short leash. Known versus unknown, breath versus motion, oddball versus artifact. The pairings are the rhythm of this work, and they are the reason wonder survives without running away with the plot. In the end, this visitor has already done what the best messengers do. It made us better listeners. It turned our attention to whispers that matter. It left us with a trail of lessons that will guide the next chase. That is enough for one season under the Sunday. The sky will send another puzzle soon. We will be ready.